All right, so the last two reactions that we're going to cover for the addition chapter are going to be ozonolysis reactions, and then we're going to look at hydrogenation reactions. But let's first do ozonolysis. And I'll give you an example using cyclohexene. And just to help us along, I'm going to include both hydrogens coming off the alkene. In an ozonolysis reaction, you first have to react your starting material with ozone, which is O3. In order to create ozone, you normally have to have an ozone generator in your lab. Ozone's kind of cool. It's this blue gas. However, there is trace ozone in our atmosphere as well. All right, so that's the first step. The second step is to reduce the ozonide that's formed. I'm not going to go over the full mechanism for that. I don't think it really helps people understand the overall transformation that well. It just confuses people. But the second step involves dimethyl sulfide, which is abbreviated as DMS. Or instead of dimethyl sulfide, sometimes you'll see zinc and water. That's the reduction step. And I will show you what DMS looks like. This is dimethyl sulfide. Very, very stinky stuff. Oops, forgot my carbon. It's got a sulfur in between two methyl groups. In general, sulfur-containing compounds stink to high heaven. So oftentimes you'll see the zinc and water used just because zinc's cheap, water's cheap, and it doesn't stink. All right, so when this reaction occurs, what happens is you'll cleave this double bond. So I essentially think of it as little scissors cutting that open. And you install an oxygen in between. So imagine this is where that cut happened, right? So if we look at it, we installed two oxygens in the position where there used to be the double bond. So when we look at this, we've created a new functional group on the top and the bottom. In this situation, we've created two new aldehydes. This is kind of a weird way of viewing this. So instead, we can kind of unfurl this and draw it as a straight chain form. And this is the exact same product. So you can use this reaction to form aldehydes and ketones. Yeah. Oh. All right. So going back to the ozonolysis reaction, you can cleave these double bonds and get resulting aldehydes or ketones. When do you think you might get a ketone rather than an aldehyde? Yeah. What if this hydrogen is some sort of alkane, right? What if it's a methyl group? If that happens, then you're going to make a ketone and not an aldehyde. So it does depend on your starting alkene. How many of you have ever noticed that old tires or old rubber starts to crack and get brittle over time? That's actually this reaction occurring just over a longer time frame, right? So if you have ozone in the atmosphere, that ozone will react with rubber and tires, slowly degrade it, cleave those double bonds, and break the structural integrity of the rubber. So that's why we observe tire rot. It's a pretty cool reaction that way. So let's do a few practice problems, and I'll show you a few variations of this reaction in practice. So the first one, we'll do ozone as step one. That's O3, followed by zinc and water. If we think about this, we're going to cleave this double bond. And do you think we're going to form aldehydes or ketones? Ketones. So we can show the resulting product. Looks like this. And to me, it looks like we're getting two identical products, right? So we could say it's two equivalents of the same ketone. So if you have a symmetric alkene, it's really nice because you don't get a mixture of products out, right? You just get two equivalent ketones. All right, let's take a look at a harder one. All right, in this harder example, we're going to have an alkene that looks like this. We're going to treat this with ozone, followed by DMS. That's the dimethyl sulfide. Does the same thing in that second step. But this time, I'm going to show the substituents coming off that top position. We've got two hydrogens there. We're going to cut this in half, just like before. So the bottom half, we're going to get a ketone. And then the top half, let me actually squeeze this up even more. We're going to get this compound. Does anybody know what that is? Formaldehyde. So formaldehyde's fairly volatile. Chances are this will just bubble out of solution, leaving you with a ketone on the bottom as your major product. So in this one, you would get a mixture of two different products. I'm just going to slide this over. But it is important to remember that the carbon that is lost as formaldehyde that typically will just evaporate out of solution. Does that make sense? All right. Yeah, that's a good question. When you do the reduction step, meaning step 2, it's lost in that step, usually as water. Yep.
What if there are multiple double bonds?
Yeah, if you have multiple double bonds, you can cleave every single one of them. Let's try that. All right, let's try this one. We've got more than one double bond. Let's try to figure out what product or products we would get out of this. So I'll give you a minute to think about it. Just to help us along, I'm going to add in the hydrogens coming off right here and here. I'll make those blue. And then I'll make our cuts with red dotted lines like that. And then we'll try to figure out what our resulting products are. Give me a thumbs up if you feel pretty confident with your answer, though. All right, it looks like most people are right on track. So let's go ahead and piece this apart, right? So the part with the two hydrogens on that side is going to become an aldehyde, right? Specifically this chunk right here. Right? That's going to be formaldehyde, which is probably going to bubble out of solution. All right, now let's focus on the other half of this. And I'm going to kind of make it close to one another. So this chunk right here is going to be basically everything from the center portion. So we will have two cuts resulting in a diketone, meaning you'll have a ketone coming off of both ends. All right, and then the last but not least chunk, we're going to have a piece that looks like this. Does anybody know what this is called? Specifically, though. It's not Tim. Give you a hint, you use it to clean glassware. Acetone, so you can create acetone from this as well. So for this specific reaction, you would create 3 different products because we have more than one double bond. So you are correct. If you've got more than one double bond, you can cleave all of them. All right, does that make sense? Yeah.
You cleave one, but not the other one.
Yeah, so the question was, can you selectively do ozonolysis on one and not another? Not really. It's too hard to control. Yeah.
If there's, maybe not ozonolysis, but is there cleaving of triple bonds ever?
Yes, and we'll cover that when we get into alkenes. So the question was, can you cleave triple bonds? Absolutely. Yeah, they just will form different products. All right, so let's jump into the next reaction. The next and last reaction for this chapter is catalytic hydrogenation. This one's pretty straightforward. You can have an alkene. You can treat this with hydrogen under ridiculously high pressures, or you can add a catalyst and do it at more reasonable temperatures. And the catalyst that's most commonly used is platinum or palladium. Usually it's palladium on carbon. So what that means is you have essentially charcoal with embedded palladium. So it's usually like 5 or 10% by mass. And when this happens, you can add hydrogen across a double bond. Specifically, the hydrogen that you add is going to add in a syn orientation, although the final product for this doesn't matter because we don't even have stereocenters. So this will be syn addition. Of 2 hydrogens. I'm not going to show the mechanism for this. It actually occurs at a interface between the solid part of your catalyst and the solution itself. So we're not going to get into it, but it helps explain the stereochemistry because essentially it docks with the surface and can only install on the same face as that surface. All right, so there's a few cool examples of this in your day-to-day life. The most common example was developed in, I believe, the 1930s, where there is a big shortage of animal oils because of World War I and World War II. And so what they did was they got a bunch of vegetable oil. And with vegetable oil, this is a liquid, right? And they decided that they could hydrogenate this using hydrogen gas and some sort of catalyst like palladium on carbon. And if you do that, you can reduce that double bond. Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, missing one. And you can form a saturated fat. Essentially, a saturated fat means that it's saturated with hydrogen, right? So what they did was they would sell this solid fat as basically a butter replacement. So many of you have probably cooked with Crisco before. Crisco is partially hydrogenated, which means they've hydrogenated some but not all of the vegetable oil so that it's not super thick. It's still spreadable, almost like margarine. Does anybody know the downside of partially hydrogenated oils? They're bad on your heart because oftentimes during this hydrogenation process, when you partially hydrogenate, you can scramble your alkenes and turn them into trans alkenes, or they're also known as trans fats. Trans fats are really bad for you. So if you buy Crisco nowadays, they're trying to change their formulation so that it's not partially hydrogenated. Instead, they replace it with palm oil or coconut oil to make it a little bit more heart healthy. All right, so let's take a look at another example. In this example, we're going to start out with a substituted alkene. We're going to react this with hydrogen and palladium. And when this happens, like I said, you're going to get syn addition, which means that both of your hydrogens must install on the same face. You won't observe any of the anti-addition product for this one. So that's again supporting the stereochemistry of syn addition. Does that make sense? All right, I did want to make a note that palladium and platinum, when they're used as a catalyst for this reaction, they're known as heterogeneous catalysts. A heterogeneous catalyst is something that doesn't dissolve well. So palladium, when you do this reaction, just settles on the bottom of the flask. You put the whole system into something called a par shaker, and it will shake it up in order to increase the surface area between the metal catalyst, the hydrogen, and your reactive alkene. These are pretty commonly done. However, there's other examples that don't use heterogeneous catalysts. So I'll show you another one that's a bit different. This next one, we still use hydrogen. We need that for the reduction. But this time we use a ruthenium catalyst. This is kind of another chunk of alphabet soup. This is called Wilkinson's catalyst. This is homogeneous or homogeneous. So you may occasionally see this used. It's a homogeneous catalyst, but it does the exact same thing as the palladium or platinum. All right, so let's try to predict what the product would be for this reaction. We're still going to install the hydrogens in a syn orientation. That top methyl group, that's a wedge, is going to be untouched. So for example, we could have both of these as dashes that were added across. That means the remaining methyl group must be a dash. Is this our only product? Nope. We could have our syn addition where both of those hydrogens that were added were both dashes. That doesn't impact that top methyl group, right? But both of these are syn addition products. What's the relationship between these? Diastereomers. So you could separate these if you want to. They have different physical properties. So it's not that much of a problem for this reaction. Yeah?
Just like how we can put plus EN, like plus diastereomer.
Not exactly. If you write plus diastereomer, I won't know what diastereomer you're talking about. If you write plus EN, there's only one possible enantiomer, right? So try to be specific with diastereomers and draw both. All right, the other cool thing with this reaction is all of the pieces that are attached to the ruthenium atom here are called ligands. They attach to the metal center. You can actually swap out these ligands and make them into chiral ligands. What do you think happens if you have a chiral ligand? Yeah, you might be able to exclusively get one stereoisomer over the other. So it's becoming a big deal, especially in the drug industry, when you want to make exclusively one enantiomer over the other. You often have to use these fancy chiral catalysts. So these ligands can be replaced with chiral ligands, which results. Oh my goodness. Maybe it is magic, though. Maybe I should have left it. All right. So these ligands can be replaced with chiral ligands, which results in one stereoisomer being favored. We're really not going to get into that. That's something that you might cover if you take advanced organic chemistry later on. Does that make sense? All right, so that's basically it for the reactions that we've covered for the addition chapter. What I like to do at the end, though, oops, yeah. Oh, I see what you're saying. There we go. So what I like to do at the end is kind of create a thought map of everything that we've covered. So we'll kind of do a summary. And then I have a bunch of practice problems. The key is already posted on the class website and in OneNote, so we might not have time to do all of the practice problems in class, but make sure you check your work at home. Is it okay if I move past this? All right. So let's go on to the concept review. The first thing I like to review is regiochemistry. And what I mean by regiochemistry is whether or not the addition was Markovnikov versus anti-Markovnikov. And I'm just going to abbreviate that. All right, so let's say we've got an alkene. We're going to be reacting it with some sort of electrophile. And I'm going to call that H in blue and then A in red. I'm just making it super generic. But in order for it to be Markovnikov or anti-Markovnikov, we're installing one hydrogen and one group that's something else. We'll call that A. Markovnikov addition, is the A position going to be attached to the more or less substituted carbon? More. So we can go ahead and we can show this as A being attached to the more substituted, the hydrogen being on the less substituted. This would be Markovnikov. However, we saw some examples where it was opposite, where the hydrogen added to the more substituted position and our new group attached to the less substituted. This is anti-Markovnikov. All right, we had a handful of reactions that did Markovnikov addition, so let's go over those. The first one was Hydrohalogenation. That was the reaction where we did HBr. No peroxides, nothing like that to mess with it. If we had peroxides, we could do anti-Markovnikov. And if you remember, we used alkyl peroxides. So the example we had here was HBr plus our alkyl peroxides. So we could change the regiochemistry for that reaction depending on that impurity, or in this case, added impurity. All right, if we think about Markovnikov hydration, meaning we want to add an alcohol, we had two different ways of doing that. We could have done catalytic, or sorry, let me rephrase this, acid catalyzed hydration. And that was where we used dilute acid and water. That again went through a carbocation and worked well. Or we could have done oxymercuration. Does anybody remember the reagents that were necessary for oxymercuration? So the first step was HgOAc in parentheses 2, along with water. And then step 2, we need to get rid of the mercury, and we use sodium borohydride. So that was a set of reagents that was used. Why would we use oxymercuration? Avoid rearrangement reactions, right? However, acid catalyzed hydration and oxymercuration, demercuration still give you they still give you the Markovnikov product over the anti-Markovnikov product. All right, if we want the anti-Markovnikov alcohol, we have to use hydroboration oxidation. All right, and hydroboration oxidation, if you remember, we use BH3 coupled to some sort of solvent, THF. You may notice sometimes on the sapling assignments, you may see B2H6. That's just a dimer of borane. It does the exact same thing. So if you see boron, you should think of hydroboration oxidation. Second step, we use sodium hydroxide and hydrogen peroxide to do the oxidation step. That gives you anti-Markovnikov alcohols. Make sense? All right, so really those were the only reactions where we could control Markovnikov versus anti-Markovnikov addition of different groups. So it does depend on whether or not we're looking for a halogen or an alcohol. Yeah?
For acid catalyzation hydration, could you use H3O plus as well?
Yeah, you could write H3O plus for acid catalyzed hydration. That's essentially the same thing. Yep. All right, now let's do stereochemistry. And by stereochemistry, I mean syn versus anti-addition. All right. And let's compare the two. So let's say I have this starting alkene, and I'm going to do addition of X. I'll make X blue and Y as the red component. And in this example, you could have X coming off as a wedge, and you could have, Y coming off as a wedge as well. Is this syn or anti? Syn. All right, you also have to watch out for enantiomers with these, right? Because they could both be dashes as well. It wouldn't necessarily give you the same product. All right, so that's syn addition. Conversely, we could have anti-addition, where one is a wedge, the other one's a dash. And just like before, we also have to watch out for enantiomers. So that would be anti-addition. So we've seen reactions that will give you either or. So let's make a list of some syn additions. We saw two different ways of making syn diols, meaning two alcohols. And this is called syn dihydroxylation. And you can do this using potassium permanganate, so KMnO4, sodium hydroxide, and you have to do this reaction cold. That was one option. Or the other option was to use the reagent that could blind you. Does anybody remember what that one is? Osmium tetroxide. So that's step one, followed by a reducing agent, which is usually sodium bisulfite and water. Either one of those will give you two alcohols in a syn orientation. Conversely, we had anti-dihydroxylation. And anti-dihydroxylation means we have two alcohols, but this time they're facing opposite directions. Does anybody remember the reagents we need for that? MCPBA is step one. That forms your epoxide. That's the three-membered ring with oxygen. And then what do we need to open that up? H3O plus or acid and water. It doesn't really matter to me which one you do, but that will give you your anti-diol. All right. We also had another one that was syn addition. This was hydroboration oxidation. And that was the borane THF, but I will make a note. It's syn with respect to the hydrogen and the alcohol. So it's a little bit weird. I'm still putting it under the syn category because the final product has syn addition of two new groups. All right. We also have some other anti-additions. Halogenation. So with halogenation, that's something where we add, for example, Br2 across a double bond. That will always give you the anti-addition. And we know that because we go through the bromonium ion and we don't ever observe any syn addition. All right. Almost done. We've got one more syn addition that we just saw. This is hydrogenation. With hydrogenation, you often use hydrogen gas, and then you'll often see palladium as a catalyst. Sometimes you'll see palladium/C, which just means that the palladium is loaded onto a carbon substrate. Another variation of the halogenation reaction that we saw yesterday and on the pod is the Halogen reaction. The Halogen reaction is when you use a halogen like bromine or chlorine, and then some sort of alcohol. However, usually that alcohol is water, and the alcohol will add anti. Does that make sense? All right, one last summary piece. It was ring opening. All right, so for ring opening reactions, that means we had some sort of three-membered ring. I'm going to put Z as the bridgehead, and Z normally has a positive charge. And we have some sort of nucleophile floating around with a lone pair or a negative charge. If you think about the identity of Z, that could be the bromonium ion, where that bridgehead is bromine. It could be chlorine, if you used elemental chlorine. It could be a protonated epoxide, so it could be an oxygen in that position. Or it could be that mercury bridgehead, like we saw with oxymercuration, demercuration. All right, which side of the ring is going to be favored when we attack it with some sort of nucleophile? The left side, right? So in this reaction, it's important to remember that regardless of your three-membered ring, you're going to favor the more substituted side. We will talk about this in a bit more detail when we get into epoxides, but for right now, this is a good rule of thumb. And you'll get a ring opening reaction where Z will be anti to your nucleophile. And essentially, it's like an SN2 reaction, right? We've got a really good leaving group, which is Z, and we're going to slingshot that open. So remember that your nucleophile prefers to attack the more substituted carbon. Does that make sense? What students in the past have done that they've told me is helpful is at the end of every chapter, they create kind of a summary sheet that they can go back and refer to when they're studying for exams and quizzes. I would really encourage you to do that as well. Whether or not it looks like something like this is completely up to you. The other thing you might notice in the back of your textbook is at the end of the chapter, he gives you a summary of reactions, and these are all the reactions that we've gone over. Students will often ask me, which ones do I need to know the mechanism for? Any of the ones that we covered in class are fair game. If we skipped a mechanism in class, I'm not going to expect you to know that for an exam or a quiz. So you can skip the ones that we didn't cover in our lecture notes. In addition to this, what I've done in OneNote is I've created a fill-in-the-blank study guide. So you can print off this OneNote page if you want and basically add in the reagents and use that as a memory tool. You can also use the flashcards on the website. You can even make your own flashcards. I've had students do that too, and they find the process of writing down their own flashcards incredibly helpful. They keep them next to their bed and go through them every night, and then before they know it, it's become second nature to them. So you're welcome to do that as well. Let's see. If you have the study guide too, the study guide also has a big review of concepts that I've included in OneNote here where you can fill in the blanks. Sometimes students find this helpful too. The key is just finding what works for you when you're studying. You can obviously tell the volume of information we're learning is pretty intense. So doing a little bit of studying every day is a lot better than trying to cram it in the night before an exam or a quiz. All right, so at the last part of lecture today, you can get started on that in-class activity. This isn't going to be graded, it's just practice for you. So for these ones, I would encourage you to do the mechanism if it's a mechanism you should know, meaning one we covered in class. And then for these ones, I'm just asking you to fill in the reagent needed to accomplish each of these transformations. But try to do as many of these as you can without notes. That way you know which ones you need to study for the quiz tomorrow.